One of the reasons I love this job is I get to introduce people who need no introduction. Our next speaker, Martin Casado of VMware.
Thank you so much. Appreciate it. Oh, cool. Thanks. Okay, guys, so today I'm going to be talking about no less than the utopian holy grail future of IT, as much as computer science will allow us to have it. And I'm going to do that within the context of OpenStack, which I think is going to be one of the key areas in which we deliver it. But I'd like to start with a little bit of background. So much of what we've been doing in infrastructure over the last two decades has been around automation. And by automation is, let me take it from the perspective of like a vendor or someone that's working on open source software, which is we've been taking bits that we've been working on, in the office or at home, and we've been trying to get them to users, and then hopefully the user just pushes a button and things work. And so there's been a lot of core technologies to make this happen, right? Virtualization is a very classic one. So virtualization will change a concept of something from hardware to software, and once it's software now, I mean, I kind of control the laws of physics for it, right? I can wrap an API around it, and I can control it as an object in a program. And another thing we've been doing has been creating global views, like cloud management systems, right? Where we'll say, oh, I've got a data center. I'm going to install software. I'm going to create a global view, and now I can do things like, fully automated placement and resource optimization and so forth. So as an industry, for IT, we've been, okay, our goal is to be like, I want to take a set of bits, you download them, you kind of do this thing, and then you have a data center. But the reality is no matter how much work we do on the back end, let's say we're developing OpenStack, and how much we do in the back office, you can't actually remove the human being from the loop and deploying and running infrastructure, right? Because there is a correct solution when we're talking about things like resource management and resource placement and resource efficiencies and so forth. There is a correct answer when it comes to HA and DR and so forth. There are technically correct answers that we can build into the system if we want. But so much about how a system used is actually driven by like what the business wants to do, that there's no way you could predict a priori what that would be. And so I'm going to call that general class of problems the policy problem. And so I think that now we have mature software, things like OpenStack, that people know how to use. And we've been talking about policy for a really, really long time. I mean, I've been working on policy for about 15 years. I've worked in the government context. I've worked in an academic context. And we've never really been able to get there. But I actually think now is the time. And so what I'm going to do with the next two pieces of this talk is first I'm going to talk about, I want to redefine policy because it's such a loaded concept and everybody has a different idea what it is. I want to kind of very clearly define a problem statement. And then I'm going to talk about how within OpenStack we can actually crack this problem. Okay? So that's my talk. My talk is A, policy is the holy grail of IT. B, now is the time. And C, OpenStack's the way to get there. Okay, so what is the policy problem? Let me take a crack at this, because again, everybody has a different idea of policy. So just let me try and define it in my own terms. So, okay, people run businesses, and there's a lot of stakeholders involved. And business is a core piece of business is IT. It's an enabler. Now, people have different ideas on how that IT should be used per business logic or per like local regulations or whatever. So you've got like security guys saying, stuff can or cannot go here, or people can or cannot have access to things. Or you've got lawyers that are like, this certain IP can or cannot be in different places. Or you've got policy wonks that are like, well, we think that, certain geographic locations, should do this type of work or not do this type of work. Or you've got laws or whatever. So you've got non-technical people, largely, with non-technical ideas. I mean, ideas of things like access and whatever to drive the business that want to dictate how the system works. Right? So normally, I mean, it would be, normally what they do is you've got these people with these ideas, and they'll go ahead and they'll write these ideas down in documents or in emails or in memos, or they'll tell them in words, and then somehow we're supposed to get this implemented on the back end. Okay, so we're all computer scientists, or a lot of us are computer scientists. So what's like a standard computer science solution to this problem? Now, the actual like science fiction ideal is some policy wonk has an idea, IT reads his brain, kind of infers what he wants to do, and just does the right thing. Okay, we're clearly not there, even just from like a core science perspective. Another thing which would be really cool is like all of those documents that these guys write and all of these rules and laws and memos, we just feed those into the system, and the system would just go ahead and consume that and then do the right thing. So we're clearly not there as a science yet either, though we're getting close. But this converges to the natural language processing problem, which is AI complete, so we don't know how to do that yet. So if you take most people that have worked in systems for a long time and say, okay, here's a problem. You've got people that want to say something. You've got a system that needs to implement it. What do? They say, well, I'm going to build some language, and I'm going to build a compiler, and I'm going to implement it. I mean, that is like the computer science solution. So I'm going to build a domain-specific language or a language that's useful to the problem. Then these guys will either write their normal documents, or maybe they're good enough to actually write it in this language. If they're not good enough to write it in the language, you'll have like some technical professional take the document, turn it into the language, and then the system will do everything else. And if you want to know what the system's supposed to do, you just look at now this kind of machine consumable declarations that have been written. That's the computer science solution to the problem. So it's really interesting at this point to ask the question, which is like, nothing I've said is new or even really interesting because we've been talking about this for like 50 years, right? We're like, oh, wouldn't it be great if we could like tell systems how to work in these kind of natural languages and just be able to declare it and have IT do the right thing. I mean, policy compilers and policy systems have been around forever. So it's worth asking the question, why hasn't anybody ever done this? Right? Why hasn't anybody ever been like, here's some high-level language, and the policy wonks and the lawyers write to it, and then IT makes sure that we're secure and that we're compliant and that we have cost optimization because it's the beam counters that actually can tell us what the cost optimization of the system is. Like when do you send traffic and where do you send traffic? Okay, so I'm going to actually I'm going to posit something. This is like, I'm not sure if anybody agrees with this, so this is literally just coming from me. But I think the reason is that every time we've tried, I've worked on 3 different policy compiler projects in 3 different organizations, every time we fail, and there's fundamental technical reasons we've failed. So I want to describe these technical reasons. So the first one is every time you've got, so the problem is the following. I've got a data center. I want to create a policy compiler. I want a compiler with a high-level language that compiles all the way down and runs the entire data center to obey the policy language. So every time you do this, you have to solve 3 problems that have been kind of intractable. The first one is just the device canonicalization problem. It's really simple to describe, which is if I'm talking to a whole bunch of gear, I need to make sure that I canonicalize that gear. So like, I'm a networking guy, so like the Cisco looks like the Juniper, looks like the Arista, or whatever. This is a problem that like the network management guys have tried to crack forever. And it's funny, if you actually look at the companies, like the engineers working on this problem, they're actually data fusion experts. They're not even networking experts because it's such a difficult problem. And you have 2 issues. One, like every time like a new device comes out, you've got to like write a whole bunch of stuff for that device. And 2, you always end up with like this lowest common denominator piece of infrastructure that sucks, right? I mean, you're basically saying I've got 3 things, but the only thing that's common about them is some basic functionality. So most software systems that try to do this have failed traditionally in the past, in any aspect, not just the policy aspect. Okay, so that's hard. The second one is also really difficult. So think about the problem of writing software for a data center, right? So I'm going to make a declaration like, if it's 5 a.m. and Martin is on, is connected, he's, probably not in a good state of mind, so don't give him access to sensitive data, right? So this is a declaration I can make. Now, the reality is the enforcement of this stuff is all over the place, right? I mean, like, I've got to enforce it at the compute and maybe at the network and the storage driver. There's a lot of enforcement points. So there's distributed state that my compiler has to manage. And in fact, any sort of compiler would have to manage all of this distributed state, and it would have to do it in a way that's transactionally complete. That means I know I can be in state A or I can be in state B, but I shouldn't like be in some weird A/B state where I don't have any guarantees because all of a sudden I may not be compliant. So distributed programming is really, really hard. And scalable transactional distributed programming is also really, really, really hard. And so anybody now that's just writing a compiler, like I get a compiler guy, I'm like, write a compiler for this, has to actually solve this very difficult state management problem. So you have the device canonicalization problem, you have the distributed state problem, and the third one is actually not super obvious, but I think it's actually the most difficult, which is if you choose a language that's independent of topology, then you actually have to solve the network virtualization problem. So it doesn't matter what language you choose. If you're talking about Martin, if you're talking about data, if you're talking about access patterns, whatever, is if it's independent of topology, something's going to have to map from this logical view down to a physical view, which actually algorithmically is taking some complex graph up here and mapping to some complex graph down there, which is a really difficult problem. So again, every time I've tried to like build one of these systems, it's like, you know, let's say forget the device canonicalization problem because I just punted it and I just built my own devices. Distributed state management's hard, so I've got to do that. But then also I've got to build this thing that's mapping these two graphs together in real time in a way that scales and converges quickly. So I would submit that the reason that we actually haven't made a lot of progress is because we haven't built real compilers that actually solve the problem because it's just been too damn hard. Okay, fortunately, we're in a new era. So if you look at the things that we've built with, like, say, OpenStack, a lot of these problems have been solved by the underlying layer. So I think now it's time for us to step back and be like, you know, we've been kicking ass for 10 years. We've built things, you know, we built OpenStack. It's great. And now it's time to move up a layer and actually solve this problem that we've been trying to solve forever. So what does OpenStack give us? Well, it gives us abstractions. Abstractions are good because now I don't have to do the device canonicalization issue, right? Somebody else solved that problem. Whoever solved the virtualization layer, for example, solved that problem. So if I spin up a virtual machine or a virtual network or storage or whatever, it's already an abstraction. It's a soft abstraction and it's canonicalized. Awesome. 2, for distributed state management, again, this is happened by the infrastructure. I have some API that spreads across the data center that manages all of this distributed state and aggregates a distributed view. Arguably, I mean, this is like the primary value of a CMS, is just constructing a distributed view and like having the ability to manipulate it in a way that's consistent. That's great. And the final one is because you have virtualization and because you have higher level abstractions, you're actually topology independent already, right? So I'm like, give me 5 VMs and a virtual network and put it wherever you want. Like I'm not talking about physical IP addresses or physical locations anymore. Everything is logical now. So I already have this abstraction from physical to virtual that I can build on top of. And so it's my belief that on top of something like this, we can actually now build our policy compiler. So I take my policy compiler, my high-level language that my policy wonks or anybody that's doing configuration or policy configuration can write to. You can compile it down to these high-level abstractions, and we are where we need to be. Okay? All right, so I'm going to talk about a specific project that I'm working on within OpenStack. Actually, there's a lot of people in this room that are working on it as well that tries to do this. Just as an example, I actually think that if we all admit that policy is kind of the next layer that we've got to automate and orchestrate, and it's kind of like a next primary technical challenge, then we need to start looking at the nature of the problem. And unfortunately, it's not as simple as let's just all build like some unified policy language that solves all the world peace. So let me talk a little bit about Congress. So what Congress is it's a project that we've been working on, which is basically building a unified policy layer. And the idea is that it runs across all pieces of infrastructure. Remember, policy isn't something that's independent. Like every subcomponent will always have a policy layer. Networking has a policy layer, and compute will have a policy layer, and storage will have a policy layer. But global declarations, especially policy declarations, always go across every piece of infrastructure. Martin may or may not access some piece of data or a certain type of compute node or whatever. So these declarations are normally at a very high level. So you need a high-level framework that goes across them. But there's kind of 2 admissions that we had when we were looking at this problem that I think that any solution has to have. The first one is the realization that every subcomponent is going to have its own policy layer, and that policy layer will be domain specific. It may choose whatever name it wants, it could use any type of language that's specific to the problem at hand, and it's going to be used for that one component. So whatever high-level infrastructure that we end up building, whatever high-level scaffolding we're building, has to be able to unify all of these subcomponents. And the second one is people hate domain-specific languages. Hate. Like every time I've worked in a system where you have users and you're creating some fancy new language for this, like it's an enormous hurdle to adoption because people don't want to learn it, especially in the early days. If there's no traction, it's almost kind of like wasted time. But it's also very difficult to understand the properties of new languages. I mean, we spend years understanding the properties of formal languages, right? And then we just start making up new languages because we're developers. I've done it many times. And then people look at this, they don't really know how to understand it. So the design behind Congress is actually really simple. If you look at most policy languages throughout history, they've all kind of looked like a variant of data log normally. What is data log? Data log is kind of like SQL, right? It is SQL, actually. So SQL is a variant of data log, which is these are these declarative languages that operate over tables at a high level. So the idea of Congress is that, you know what we're going to do? We're going to represent every system as a set of tables, just like you would in a database, whether it's network or computer storage or whatever it is. And then you can make declarations at a high level to query these or join these or manipulate these in any way that you want. And anytime you want to extend one of these, like add a new type of infrastructure, a new policy language, all you do is you expose it in tables, and it'll allow declarations that write over it. So the goal now is within something like OpenStack, or OpenStack in particular in this case, is you have a layer that allows declaration at a high level that you can just focus on from a consumption standpoint. You know, whatever tools are needed to like write these policies, to map from things like PCI documents or internal policies down to it, and then hopefully it can be enforced globally. So I'm actually just going to end on this slide to say, and this is just a small point, that, I mean, right now, if you look at the nature of policy in systems that claim to do policy, they're actually really simplistic, right? I mean, often they're overblown ACLs, or they're simplistic constraint-based placement algorithms. But there's no reason that we can't make it so it actually is almost a literal translation of some of these higher-level documents. I just have an example up here. And remember, when a policy system touches a consumer, there are many actors within that consumer that want to write to it, whether it's a developer or an operator or a compliance officer or a lawyer. And we want to be able to answer sensible things about it. Like if I've got a company running OpenStack and there's one policy document, there's many people that have touched it, and we want to be able to answer questions like, can A talk to B given all of the policy that's going on? Or what happens, for example, if I change this policy? Does it impact the level of the system? Or let's do some what-if testing on test dev or constraining or whatever. And like, we should only be limited. We should only be limited by kind of the laws of the language. Like, I should be able to give you a language, and I should be able to give you a namespace, and you should be able to declare anything within those two things. And hopefully, if we drive this far enough, we'll stop thinking about things like compute and storage and network, and we'll stop thinking things like implementation, geographic locations, and we'll only think at this much higher level. And I think as soon as we've done that, we've kind of arrived. We've basically pushed IT to the limits of computer science. Computer science, the limits of computer science for interacting with human beings is basically some domain-specific language with a namespace people care about, and no implementation shows up there, none. No IP addresses, no ports, no specific machines, nothing in the implementation shows up, and now we can understand and define the entire system by this language. And so that's kind of the goal that we want to get to. So with that, I will conclude my talk, and I think we don't have time for questions, so I'll get off. Thanks so much, guys.